Vanadium Redox Flow Batteries Part 1. Energy Storage Part 3. Vanadium Redox Battery. The Vanadium Redox Battery, that is VRB, also known as the Vanadium Flow Battery VRFB or Vanadium Redox Flow Battery VRFB, is a type of rechargeable flow battery. It employs vanadium ions as charge carriers. The battery uses vanadium's ability to exist in a solution in 4 different oxidation states to make a battery with a single electroactive element instead of 2. For several reasons, including their relative bulkiness, vanadium batteries are typically used for grid energy storage, that is, attached to power plants / electrical grids. Vanadium redox battery specific energy is 10 to 20 watt-hour per kilogram. Energy density is 15 to 25 watt-hour per liter. Charge-discharge efficiency is between 75 to 80%. Time durability is 20 to 30 years. Cycle durability is greater than 12,000 to 14,000 cycles. Nominal cell voltage is from 1.15 to 1.55 volt. Request: it is hoped that this session is going to be useful to you. Please press like. Please subscribe. Advantages: VRFB's main advantage over other types of battery: no limit on energy capacity, can remain discharged indefinitely without damage, mixing electrolytes causes no permanent damage, single charge state across the electrolytes, avoids capacity degradation, safe, non-flammable aqueous electrolyte, wide operating temperature range including passive cooling, long charge-discharge cycles lives 15,000 to 20,000 cycles. They are also cheaper to make because they don't require precious lithium. VRFBs hold their juice, that is liquid electrolyte, separately from the main battery. To increase the capacity of the VRFBs, just add more tanks of liquid electrolyte to the main battery. Disadvantages: VRFB's main disadvantages compared to other types of battery: relatively poor energy to volume ratio compared to standard storage batteries, relatively poor round-trip efficiency, high weight of aqueous electrolyte, relatively high toxicity of oxides of vanadium, a schematic design of a vanadium redox flow battery system. The same diagram but little bigger. You may refer to it as per your convenience. Membrane. A vanadium redox battery consists of an assembly of power cells in which two electrolytes are separated by a proton exchange membrane. This is the proton selective membrane. It is also called ion selective membrane. The electrodes in a VRB cell are carbon based. This is the negative side of electrode and this is positive side electrode. Electrodes. The most common type are carbon felt, carbon paper, carbon cloth and graphite felt. Recently, carbon nanotube based electrodes have gained marked interest from the scientific community. Diagram of a vanadium flow battery. Little bigger diagram for your reference. Electrolytes. Both electrolytes are vanadium based. The electrolytes in positive half cell contain VO2 with single charge and VO with double charge ions, while the electrolyte in the negative half cell consists of vanadium ion with 3 positive charges and vanadium ions with 2 positive charges. Electrolytes. The electrolytes can be prepared by several processes including electrolytically dissolving vanadium pentoxide V2O5 in sulfuric acid H2SO4. The solution remains strongly acidic in use. Membrane is another critical component. The most common membrane material is perfluorinated sulfonic acid PFSA or Nafion. However, vanadium ions tend to penetrate the membrane and destabilize the cell. A 2021 Chinese study found that this penetration is reduced with hybrid sheets made by growing tungsten trioxide nanoparticles on the surface of single-layered graphene oxide sheets. These hybrid sheets are then embedded into a sandwich-structured PFSA membrane reinforced with polytetrafluoroethylene, that is Teflon. The tungsten trioxide nanoparticles also promote proton transport, offering high coulombic efficiency and energy efficiency of more than 98.1% and 88.9% respectively. Operation. The reaction uses the half reactions. VO2 with positive charge plus 2H with single positive charge plus electron becomes VO plus 2 electric charges plus H2O, and EMF is 1 volt. Second half reaction is vanadium ion with 3 positive charges plus electron becomes vanadium with 2 positive charges, and the EMF is minus 0.26 volt. Other useful properties of vanadium flow batteries are their very fast response to changing loads and their extremely large overload capacities. How do vanadium flow redox batteries work? This diagram explains the working. Little bigger diagram for your reference. During the discharge cycle, vanadium with 2 positive charges is oxidized to vanadium with 3 positive charges in the negative half cell, and an electron is released to do work in external circuit, either DC or for AC systems through an AC-DC converter. In the positive half cell, vanadium ion with 5 positive charges in the form of VO2 positive charge accepts an electron from the external circuit and is reduced to vanadium with 4 positive charges in the form of VO with 2 positive charges. Hydrogen ions are exchanged between the two half cells to maintain charge neutrality. The hydrogen ions diffuse through the anion or cation permeable polymer membrane that separates the half cells. Operation. Studies by the University of New South Wales have shown that they can achieve a response time of under half a millisecond for a 100% load change and allowed overloads of as much as 400% for 10 seconds. The response time is mostly limited by the electrical equipment. Unless specifically designed for colder or warmer climates, most sulfuric acid based vanadium batteries work only between about 10 degree and 40 degrees centigrade. Below that temperature range, the ion infused sulfuric acid crystallizes. Round trip efficiency in practical applications is around 65 to 75%. Proposed improvements. Second generation vanadium redox batteries may approximately double the energy density and increase the temperature range in which the battery can operate. The vanadium bromine and other vanadium based systems also reduce the cost of vanadium redox batteries by replacing the vanadium at the positive or negative electrolyte by cheaper alternatives such as cerium. Typically, perfluorinated sulfonic acid (PFSA) is used as the separator membrane. However, vanadium ions can cross the membrane and destabilize the battery. Researchers grew tungsten trioxide nanoparticles on the surface of graphene oxide sheets and embedded them in a polytetrafluoroethylene reinforced sandwich structured PFSA system. This reduced penetration and promoted proton transport, yielding coulombic efficiency and energy efficiency of greater than 98.1% and 88.9% respectively. Specific energy and energy density. Current production vanadium redox batteries achieve a specific energy of about 20 watt-hour per kilogram of electrolyte. More recent research indicates that the use of precipitation inhibitors can increase the density to about 35 watt-hour per kilogram, with even higher densities made possible by controlling the electrolyte temperature. The current specific energy is quite low compared to other rechargeable battery types. For example, lead acid 30 to 40 watt-hour per kilogram and lithium ion 80 to 200 watt-hour per kilogram. However, using precipitation inhibitors would place vanadium redox batteries on par with lead acid batteries. Applications: VRFB's large potential capacity may be best suited to buffer the irregular output of utility-scale wind and solar systems. Their reduced self-discharge makes them potentially appropriate in applications that require long-term battery storage with little maintenance. Response times well suited to uninterruptible power supply (UPS) applications where they can replace lead acid batteries or diesel generators. Fast response time is also appropriate for frequency regulation. These capabilities make VRFBs an effective all-in-one solution for microgrids, frequency regulation and load shifting. Largest vanadium grid batteries: a 200 megawatt 800 megawatt hour vanadium redox battery is under construction in China. It is called Dalian battery. It is expected to achieve its full capacity in near future, and its 250 kilowatt / 1 megawatt hour first stage was in operation in late 2018. Request: it is hoped that this session was useful to you. Please press like. Please subscribe.